Good morning to everyone. My name is Emanuele Sonfiti. I'm from NTNU, and my supervisor is Professor Berto. Actually, this work is the second part of a main project. The first part was presented at the virtual conference, and it's about flexible graphite. The first part was about the mechanical properties of flexible graphite, and this part is about thermophysical properties. Actually, these two parts are the beginning of a larger project, which involves our research group together with the CERN, so European Center for Nuclear Research, and the goal of this project is to characterize this material, to have a very in-depth knowledge of this material, both from a mechanical point of view, thermophysical point of view, and also dynamical point of view. But I will show you the applications of this material at the end, and also the application that CERN wants to apply it for. So the question is, what is flexible graphite? I don't know how much you are familiar with graphite, maybe less with flexible graphite, but what we used to call graphite is artificial graphite, and it can be polycrystalline or pyrolytic graphite. The manufacturing process is different. The polycrystalline graphite comes from petroleum coke or natural pitch, while pyrolytic graphite comes from pyrolysis of hydrocarbons at high temperatures. And pyrolytic graphite can be highly oriented or randomly oriented. More specifically, as you may know, graphite is made of carbon layers that are stacked in this way. They are like this bidimensional lattice of carbons, so they have like an inherent anisotropy within the material. And as metals, graphite can be polycrystalline, and the grains can be oriented randomly in polycrystalline case, but they can even be like a main orientation. It's an average orientation of the grains. But for example, for pyrolytic graphite, this property is stronger. So this type of graphite is the nearest approach to a large single crystal of graphite that is available for testing, for example. But flexible graphite is not part of artificial graphite. It comes from natural graphite. Natural graphite, as you can see in this image from SEM, is purely crystalline and is made of, it's in a shape of flakes. These flakes are purely crystalline and basically are a layer of carbons stacked together. And to make flexible graphite, we have to intercalate these flakes and make them to expand upon a huge amount of heating, and they can expand over 300 times of the original thickness, and they assume this particular shape. These are called worms, and they can have this kind of honeycomb cellular structure, which comes from the hexagonal shape of the typical graphene layer. So these are the basic units of this powder that, without any additive binder, is compressed at the beginning and then rolled, which is a heavier step of compression. And during this compression, these worms, they are compressed, of course, and they interlock among themselves, and they tend to be orientated in plane direction, increasing the anisotropy of this material, which is a strong typical properties of flexible graphite. So the density increases, and up to a certain threshold of density, so that's 0.4, 0.5 gram to cubic centimeter, we can call this material compressed expanded graphite or graphite compacts. And it can be even, it's still isotropic in this part, and it gets more anisotropic after a certain threshold here. So the worms are these structural units, and they are entangled, and actually they can be called the deformation units, because they lead the overall mechanical behavior of the material. So we can say that flexible graphite is a porous material, and is only carbon, graphite, and air inside, and is strongly anisotropic. From a commercial point of view, we can have different shape of this flexible graphite. The most common is foils with different thickness and densities, but we can have also yarns and other different customizable shapes. It's very easy to make flexible graphite. So, as I said, the strength is due to the interlocking, only the friction forces between the contact points of these compressed worms. And we can define how we can define the anisotropy. We can define the anisotropy in different ways. For example, we can use the thermal conductivity of this material. So we can say that anisotropy is the ratio between the conductivity in the in-plane direction of this material to the through-plane, to the thermal conductivity in the through-plane direction. And in this work from Cesar in 2005, has been found out that there is a strong analogy between conductivity and modulus. So as we can define also anisotropy by means of the modulus. So modulus in the in-plane direction and through-plane direction. Going ahead, there are three approaches basically in literature that can be found how to model this thermal conductivity, which is fundamental to understand the microstructure of this material. We can have this approach, which is the Hutchins-Strickland model, is for two phases material, as this formula, for this formula. The second one is a percolation theory, and the last one is a well-known rule of mixtures. All of this model involves the mix of two phases, so the solid content, that the contribution of the solid part to the material. So basically the density, of the bulk density of the material, together with the orientation of the deformation units that we saw in the previous slide. So density and orientation combined together, they can model this material. And actually the Hutchins-Strickland model seems to be the best to approach the best approach to model this material in the whole range of density. But let's go to some data from literature. We see in the left plot, we see the thermal conductivity in the in-plane direction, and here we see the thermal conductivity in the through-plane direction. We see that literature data are a bit divided between those that analyze data in the low range, so in the range of graphite compacts, and those that analyze flexible graphite in the high density range, here and also here. So this plot here is a bit a mess, but I will explain soon. Okay, so the thermal conductivity here can be even 2 orders of magnitude higher than, the thermal conductivity in the in-plane direction can be even 2 orders of magnitude in the in-plane direction with respect to the through-plane direction. So this this show the high anisotropy of this material. So the data from literature are in agreement. Here I even show some data from datasheet, because actually literature on this material is very scarce, it's very poor. So I struggled a bit to find some data, and also when I find something, it's difficult because the density is different, because the thickness is different. So it's not easy to compare the data. Here we can see that the thermal conductivity in the through plane, at the beginning it increases, because at this stage the material is still not interlocked. So together with the interlocking, the conductivity increases and then decreases, because the deformation unit tends to be orientated more in the in-plane direction. There is only one set of data which seems to be a bit out of the trend, but maybe because of different measurement technique, and actually is one of the newest, so from 2014. So about thermal conductivity, a lot of work has to be developed in the future, especially for thermal conductivity against temperature. There is no literature data available except data from datasheet, and I found out that these data here are for flexible graphite. The thermal conductivity in the in-plane direction, so here, fall exactly in the range of the polycrystalline graphite. So we can see that here, this hybrid curve, we have pyrolytic graphite. The thermal conductivity measured in the in-plane direction of pyrolytic graphite, which is strongly oriented, and it represents like an upper bound of the thermal conductivity that can be reached by some graphitical materials. And here we see the through plane measurement for the pyrolytic graphite, which is the lower bound. So all the data seems to fall here and here, so in this range defined by pyrolytic graphite, and this is also a proof that we can, through temperature, we can model this material as a mix both of the solid content, but also of the orientation. So the orientation of this structural unit is very important for model this material. About the specific heat capacity, there is only one data for classical graphite, and it's at room temperature. So there is not that much to say. This is the value, so 850 joule per kilogram Kelvin, and it's pretty higher than that of regular graphite, so polycrystalline graphite. And the specific heat is still comparable to that of like common metals, for example copper and aluminum, and it can be greater here. And usually, okay, here there are a lot of models about graphite and how to model the specific heat capacity against temperature, and usually it's a polynomial regression. Finally, the coefficient of thermal expansion is very important. Here we have the thermal expansion in the in-plane direction, and the values are very close to 0, so they go from -1.5 to 1.5. And for example, this is a commercial flexible graphite, and it has no thermal expansion in the in-plane direction. But in the through plane direction here, the value can be even 1 order of magnitude higher. But in this case, even if they are higher, they are comparable to that of some isotropic metal like copper and aluminum. So we can say that this is a very strong property of this material. Let's see shortly the melting point of these materials. For example, graphite. Actually, it doesn't melt at atmospherical pressure, but it vaporizes at 4,800 Kelvin. So it's very high temperature. It's very high compared to copper and aluminum. And still, flexible graphite has a very high melting point in inert atmosphere, because the risk of graphite when you go for high temperature is the oxidation. So it has to be in an inert atmosphere. Other relevant properties: electrical resistivities, that is very linked to thermal resistivity. Compliance, which is very important because this is a material which is a bit soft, and improve the thermal transfer, the heat transfer with the other material. Thermoelectricity, and piezoresistivity, which is a pretty new work. The applications in a mechanical field, there aren't so many applications so far. We see it in sealing and gasketing and in vibration damping, but this material is mostly used in cooling of microprocessors or in electrical application for fuel cell electrodes, resistive heating elements, and sensing. But as I said at the beginning, we're now starting to study this material also from a mechanical point of view, because we need a fast heat dissipation and a thermal shock, because this material is a core part of the beam damper of the new high luminosity large hadron collider that is going to be developed in the next few years at CERN. So basically here we have a lot of this stacked layer of foils of graphite, and then we need to know, for example, equation of state of this material at very high temperature, and this is like the starting point of a huge work that is going to be to start now. So thank you for your attention.